All right, guys, let's do another example where we're thinking about vector equations. So I want to find the vector equation of the line through these 2 points. So I know that to do a vector equation, I know that I am going to have an equation. In this case, I am in R3 because there are 3 components in those points. So I'm in R3, which means I have an X, Y, and Z, X, Y, Z. And because this is a line, that means I'm going to have a one direction vector. So this is going to look like some point plus t times the direction vector. So these are the things that I need. I need a point and I need a direction vector. Well, I clearly have 2 points. Either one of them can go there. It doesn't matter. That just has to be some point on the line. Now, for my direction vector, I remind you, a direction vector is going to be a vector that is parallel to my line. So my line here, I have point 1, I have point 2. My line is a line that goes through both of those points. Now, if I were to draw a vector, oops, I don't know what just happened there. Sorry about that, give me a second. Okay, now if I were to draw a vector through those 2 points right here, so I have my line that just goes through those points. There's point 1, there's point 2. Notice if I draw a vector through those 2 points, that vector is on the line clearly, and so therefore parallel to the line. So a vector between 2 points on a line, and it could actually also be a plane, it really doesn't matter, is parallel to that line or plane, and thus a direction vector for that line or plane. Okay, this is kind of important. You should have that in a place where you can look back at it and easily see it. So what that means is to find my direction vector here, I really just have to find the vector through my 2 points. Now I remind you, a vector through 2 points, I find by doing terminal point minus initial point. So I'm doing P2 minus P1 here, 1 minus 2, 2 minus 1, 5 minus 2. To get -1, 1, and 3. And this right here can be considered my direction vector. So my equation here will be x, y, z is equal to, it does not matter what point, so I'm going to go with 2 and 2, plus t times my direction vector, -1, 1, 3. Or I could have used the other point. My other point was 1, 2, 5. So I could also say 1, 2, 5 plus t times that direction vector. So it doesn't matter which point you use. Okay, so the next part of this question is, wait, so actually let's put a square on that. That's my final answer. I could have done that or I could have done this. It really doesn't matter. You don't have to write both of them. My next question is it possible to write a general equation for this same line? And this is an easy answer. If you had to guess, so what would you guess? Hopefully you're saying no. The answer here is no. because this line is in R3. No, this line is in R3. And we have said that general equations for lines can only be used to describe lines in R2. This line is in R3. It has the three variables, the x, y, z, three components in my vector. And general equations can only be used to describe lines in R2. So that's my answer to this question. Next question is, so we know how to figure out if a point is on a line when we have the general equation. You guys did that back in, I don't know, like Sec 2, Sec 3, a long time ago. So how do we determine if a point is on a line when we're using the vector equation for that line? So the next question is the point P018 on the line? And the answer is if there is some t value that makes the equation true. So we need to check, is there a t value that when I replace x, y, z with 0, 1, 8, it's true? So in other words, is there a t value that causes x is equal to 0, y is equal to 1, and z is equal to 8? Now, it's often easier to think about this when we have the parametric equation instead of the vector equation. So that's the first thing I'm going to do. I'm going to rewrite my equation, my vector equation for the line, as a parametric equation, or rather as parametric equations. So this is basically like just getting rid of the little brackety things for the vectors and kind of writing the x equals the y equals and the z equals separately. So my x would be 2 minus t, my y would be 1 plus t, and my z would be 2 plus 3t. Now notice I went with the first equation that I used up there. I could also have gone with the second equation that I used. The x is equal to 1 minus t. Y would be 2 plus t, and z would be 5 plus 3t. And that would give me the same equation. I mean, it would give me equations for the same line. So now I want to, after I've rewritten his parametric equations, I want to plug in x, y, and z and solve for t. So for my x value here, I'm going to get that 0 is equal to 2 minus t, which means that in order for x to equal to 0, t has to be equal to 2. For my y value, one is equal to 1 plus t, my t would have to be equal to 0. Meaning the t that makes x 0 and the t that makes y 1 are different t's. If I were to continue going on with z here, then I could say z, 8 is equal to 2 plus 3t, which would give me 3t is equal to 6. So this would give me t is equal to 2. So notice here, even though these two t values are the same, the t value that would make y equal to 1 is different. So there's not one t value that makes x, y, and z the same. So here, the resulting t values are not all the same. So no, the point is not on the line. Now, What this means is, and I want to make this clear in case this looks a little bit different sometimes, which it might, which means there is no one t value that I could plug in that would give me 0, 1, 8 as a solution. So there is no one t value that I could plug in that would give 0, 1, 8 as a solution. Okay, so let's go on. Let's look at just one more point and make sure that we understand how to determine if a point is on a line. What about P0, 3, 8? Okay, so we're gonna do the same thing. So here I would say X, I would have 0 is equal to 2 minus t, which would tell me that t is equal to 2. Y would be 3 is equal to 1 plus t, which would again give me t equals 2. And Z would be 8 is equal to 2 plus 3t. So notice I'm still just using those parametric equations that I wrote. And this again would give me t is equal to 2. So notice all of the t values are the same here. What this means is if I plug in t equals 2 up there, the result is 0, 3, 8. Plugging in t equals 2 gives the point 0, 3, 8. So yes, it is a point on the line. All right, so we've seen how I can find the equation of a line between 2 points, and then a vector equation of a line between 2 points. We've reminded ourselves that vector equations only exist to, general equations only exist to describe lines in R2. So this vector equation that I came up with for a line in R3, I could not write the equivalent general equation, and we've seen how to determine if a point is on the line when what we have is the vector equation for that line.